I'm starting again. Okay, so here what we have is this. We have 4 times x minus 2 times y is 12. Remember, I didn't sketch the graph till on the next slide, but even without that, we already said that non-vertical lines pass the vertical line test. So they are functions. They define functions. In other words, if you have an equation in x and y whose graph is a non-vertical line, you get a function. You get y as a function of x. Let me show the graph anyway. This is what the graph actually looks like. It's a non-vertical line, so it passes the vertical line test. Boom. Okay. And I know the graph was on the next slide, but really, based on what we saw already, you should see that, oh, well, the graph of this is a non-vertical line, so we're good. We have a function. We can get y in terms of x here. Namely, we solve for y in terms of x. That's what I'm doing here. And now we have our formula. That is, we have y in terms of x. So if I let f be the function, we have this. I'm replacing y with f of x. I do have y is a unique expression of x. That's actually how the book does it. So let me just erase that. I gotta fix these notes. There we go. It's not wrong that I have it there. I'm just not really going into that. So anyway, so we have f of x is -6 plus 2x. But that tells us how to get our output from our input. If x is your input, right, you plug it into the formula and you get f of x. I'm actually doing that with 1 here. So f of 1 is -4. So this is saying that if I take 1, plug it into the function, the output I'm going to get would be f of 1, right, which is equal to -6 plus 2 times 1. Bear with me. Oh my goodness. That's all right, I guess. Which is equal to -4. That's all I'm saying here. I do this for 1, as you can see. I'm also doing this for 2, okay? Right? F of 2 is -6 plus 2 times 2. And so here, let me do that over here, actually. So for 2, you plug that into the function, right? We get back our output, f of 2, as you can see. And in this case, f of 2 is given by a formula, which is -6 plus 4, -6, plus 2 times 2, plus 2 times 2. And doing so, what do we get? We get -6 plus 4, which is -2. Just trying to write out what's happening up here. And of course, you could do this with other numbers as well, because we have a formula. If we were to graph it, as on the next slide, each point can be thought of as being of this form, right? Remember, when you have a function, right, your input is the x-coordinate. Your corresponding output is the corresponding y-coordinate. All we're saying here is x goes in, this comes out. And this is our formula for f of x. Sorry, let me just wait a second. I don't want to go too fast. But this is, again, the graph. Again, I'm just writing this stuff to help illustrate. Notice the point 30 is on this line, right? 30 is on the line. And so because of that, that tells us f of 3 is 0. The x-coordinate goes to the y-coordinate. Same thing with 4, 2. Okay? 4, 2 is on the line. So as we just saw, f of 4 is 2. Okay? Yeah? Someone have a question? Remember, I can't see the chat when I'm lecturing, so, okay? Why did I pick 1 and 2? I just picked 1 and 2 like randomly, okay? Someone asked in the chat, why am I picking 1 and 2? That's just kind of randomly, that's all. Oh, sorry. Remember, oh my goodness, random, there we go. I misspelled. Okay, but hopefully that helps, so. I mean, I could have picked any 2 numbers I want. Here I picked 3 and 4, so. Question? Any other questions? Let me do this actually. I'll put this out. I always like to do this. You know, I can't see your faces, so I have to keep doing these polls. I really want to make sure everyone is learning this. So much fun. Okay, let's keep going then. So, okay. All right, so from here we have this here, and the 3 and 4, I'm really just choosing randomly, mostly because you can see 3 and 4, those points here. I can't see 1 and 2 here, so although 2 I guess we can see. But here you can see that 2, the point 2, negative 2 is on the graph. So that's how another way of seeing that f of 2 is negative 2. That's another way of seeing it. Okay. All right, now these are just some more examples. This one, we're going to have a non-vertical line, okay? Mostly because we have x and y in here, right? If you remember, the standard form of the equation for a line is ax plus by equals c. A, b, and c are numbers. A and b cannot both be 0. So, and we do actually have that here. I know we have subtraction, but remember, you can think of subtraction as adding the negative. So we do have that here. So this is a non-vertical line. It's a line by what I said. It's a non-vertical line because we have x and y. So the graph of this is a non-vertical line. So we have a function. We have y as a function of x. And I'm basically getting that function. I'm solving for y in terms of x, as you can see. If f is our function, we have f of x this way. So f denotes the function. And this is basically saying that our graph, right, our function is given by this formula. And the points on the graph all look like this. Where f of x is this. Here's another example. Here's our equation. Now, does this graph pass the vertical line test? It turns out it does. It's actually on the, the next slide. But basically, what we can do is we can solve for y in terms of x. I mean, you can even do that anyway, I guess. But solving for y in terms of x, we divide both sides by x. Get this? Okay? And our function fn, if we call it f, we have this. So our function f of x is 1 over x. And the graph does satisfy the, the vertical line test. That's what this graph is. I know as you get closer to the y-axis here, It looks like it doesn't pass the vertical line test, but believe me, it does. Okay, so we have this function here. Y equals 1 over x, or again, if we let f denote the function, we have this 1 over that number. Okay, that's fun. All right, so we have that. Okay. Remember also how from relations, and even from correspondence diagrams, we can get domains, right? Relations have domains, and if the relation is a function, we have the domain of a function. You can get the domain of a function as well. You could get it from the graph. If you have it in relation form, you can get that. I mean, next time I'll show you how to get the domain from the graph. Usually in the past when I've taught this class, I've done that first. I'm trying something a little bit different. But you can get the domain of a function from an equation. And namely, you just have to, it can be tricky. It's not always obvious. But there's basically some rules we're going to follow. Namely, the denominator can't be 0. You never divide by 0. We also, I think I've seen this before, never take the square root of a negative number. When you take the square root of something, it has to be non-negative, meaning greater than or equal to 0. And in number 3, I'm kind of putting these two together. If your denominator is of this form, where w is just some expression in x. It could be x plus 1, x minus 4, whatever. You want all x so that the radicand w here is positive. That's if this is in the denominator. If it's not, then in a sense you just go to rule 2, it just can't be negative. But here I'm saying it can't be 0 either. Okay, let's keep going. So to illustrate this, to illustrate number 1 then, we already had y equals 1 over x. This gives y as a function of x, right? You can't divide by 0. So the domain is all numbers except 0, as you can see. It's everything except 0. This one, the domain, it's all numbers such that x is non-negative, right? Number 2, we never take the square root of a negative number. That's what I'm doing here. Excuse me, we're finding the domain, so that does not happen. Okay? So the domain is all x such that this is true. Or as an interval, we have this. Okay. And this is just an example illustrating rule 3. In this case, we're taking the square root of 2x minus 4. So we want to make sure 2x minus 4 is not 0. Or excuse me, let me say it again. It just can't be, it has to be positive. 2x minus 4 has to be greater than 0. So we want all x. So 2x minus 4 is greater than 0. If you went back to this, your w here would be 2x minus 4. It's in the denominator. Okay? So we solve this inequality. Okay? Now, from here, okay, what we're going to have is, we just get x, so we're using what we did in 1.5, right? We want to get x, so we add 4 to each side, okay? That's what I'm doing. Then we're dividing both sides by 2, and we get x is greater than 2. So we're solving this inequality, we're finding all the solutions, and the domain then is all x such that this is true. Such that x is greater than 2, same as saying all x in this interval. So we have the domain of this function. Let me stop the recording.